Alright, welcome back everyone. Today we're going to be doing something fun, which is we're going to be learning how to use Z80 Assembly Language to print stuff on the screen. And it's always exciting to print stuff on the screen, particularly if you haven't printed anything on the screen using assembly language yet. This is going to be really exciting for you because it's always exciting the first time you print anything on the screen. As we all know from our first Hello World programs we all made in BASIC decades ago. And of course we're going to need to be able to print stuff on the screen in order to make our games, right? So before I get started, I just want to show you the resources that I'm using to learn how to do these tasks myself. And the first resource is this one here, which is kind of a training document, a tutorial that was created by someone named Darryl Sloan, and it's called First Steps in Z80 Assembly Language by Darryl Sloan. And Darryl Sloan, I think, is pretty well known in the Spectrum community, at least in the ZX Spectrum Next community, because he has created these tutorials. He created this written tutorial for Z80 Assembly Language, as well as he has a YouTube tutorial series on assembly language as well. And he also created a printed tutorial for programming in BASIC that is in, I think, 8-Bit magazine. And I think I actually have that magazine. Just hold on a second, I'll grab it. So here is 8-Bit magazine. And this one is issue number 10. And I think this contains maybe part 2. Yes, part 2 of Darryl Sloan's tutorial for programming in Sinclair BASIC. Actually, Next BASIC for the ZX Spectrum Next computer. And here it is right here on page 38. Coding a game in Next BASIC, part 2. And I'm sure I have part 1 here somewhere. I have my trusty crash binder with all my little mini magazines in it here. I've actually filled this one up with all my magazines because I forget what I order, so I end up getting duplicates of the same magazine, which I guess is okay. And I'm sure I have the magazine that contains the first part of his article as well, which is right here. 8-Bit magazine, issue number 9. And we can see in here, Coding a Game in Next BASIC, part 1. So today's video is not about Next BASIC, it's about assembly language. But I just wanted to give credit to Darryl for creating this fantastic tutorial, which I'll be going through. And I've started going through it already to something wrong with my camera doesn't seem to want to focus today. So I've been going through this tutorial by Darryl Sloan to continue on in my journey of learning to program in Z80 Assembly Language. And it's really a fantastic tutorial if any of you prefer learning, for example, by reading text rather than by watching YouTube videos. Then I encourage you to download this PDF file, which is freely available online. And even if you do enjoy learning by watching videos, I still think it's worthwhile to download this printed tutorial, because then you'll have a record of it in printed form, as well as it also covers information that I won't be taking a look at in today's video. So one more thing I wanted to mention is that I believe that at least parts of Darryl's tutorial are based on another terrific tutorial that was created by another well-known person in the ZX Spectrum Next community, and actually the Sinclair Spectrum community, which is Jonathan Cauldwell. So this tutorial created by Jonathan Cauldwell, which is called How to Write ZX Spectrum Games, and this is version 1.1, which I believe is the most recent version. And like I said, I believe that Darryl Sloan's tutorial was based at least partially on Jonathan Cauldwell's tutorial. So, but I haven't actually read Jonathan's tutorial yet, although I'm sure it's excellent and I do plan to read it, but I just haven't had a chance to go through it yet. So I just wanted to take note of those two resources that you might find useful to go through if you want some printed material that will cover the information that I'll be covering today as well. And like I said, both of these documents are available in PDF form. They're freely available online, and you can go and find them and download them and read them for yourself. And I've also uploaded copies of these two documents to my SpriteWorks Facebook group for my Patreon subscribers in case they want to download them there instead of finding them on the internet. But as I say, both of these documents are freely available on the internet, so you can find them there. And I'll try to find some links for them that I can put in the video description down below as well. So as I mentioned, today we're going to be looking at printing stuff to the screen on the Sinclair Spectrum computer. And we're not going to be printing fancy graphics today. Unfortunately, we're not quite at that point in our game development journey yet, but we are going to be learning how to print both text characters as well as numbers. And it's not quite as straightforward to print these things in assembly language as it is in BASIC, for example. As you probably know, it's very easy to print stuff to the screen in BASIC. All we have to do is use a print command and you can print whatever you want on the screen as far as text and numbers go. But it's a bit different in Z80 Assembly Language, and it's a bit more interesting, although a bit more complex. However, luckily we do have some tools that make the job a lot easier for us by way of ROM routines that we can call to help us do this printing for us. And if you're not already familiar with ROM routines, I know we've looked at it a bit in some of the previous videos, but ROM routines are subroutines that are contained within the ROM memory of the computer itself. And if you're not really familiar with that, you could watch the video that I made on computer architecture, which explains about the different parts inside the computer, including memory, the ROM memory, and the RAM memory, and how it works. But today we're going to be taking a look at doing some printing to the screen. So if you're ready, let's go ahead and get started. Alright, so before we take a look at how we can actually go about printing stuff to the screen, we need to talk about how the screen on a Sinclair Spectrum computer is divided. And when I say how the screen is divided, I'm not referring to the way that you might be familiar with, where you see a tape loading screen and you see it printing line by line and thirds by thirds. That's the pixel display that's showing up on the screen. And it is, as you probably know, divided into thirds, and each third is divided into lines, and each line is divided into the pixel rows. So that's not what I'm talking about when I'm referring to how the screen is divided. But specifically, I'm talking about how the screen is divided into two main print areas. Or, as we're going to see in a moment, how the screen is divided into two output channels. These print areas are referred to as output channels in Z80 Assembly Language, and those different screen areas or channels consist of these two parts. If you take a look at the emulator here I have on my screen, this upper part that we see, which is normally where the output from our basic program prints stuff to the screen, this is the upper part of the screen. And there's another part of the screen which consists of these bottom two lines down here where the computer prints messages, and that's also where we type in our basic instructions. So if I were to go over here to my assembler and begin typing in a basic program, for example, this would be using this bottom part of the screen, which consists of two lines, which is known as output channel 1. So today we're going to look at how we can print to either one of these channels, channel 1 and channel 2, which is the bottom two lines of the screen, as well as the large top portion of the screen. So let me go ahead and open my assembler here. And I'll just move this over here. There, so now we should be able to see both our emulator window and our assembler window. So now let's take a look at how we can print to the screen using Z80 Assembly Language. So first of all, let's start our assembly language program by typing our org statement. And I'll just put org 30,000. So our machine code program will start at memory address 30,000. And the first method we're going to look at printing is how to print a single character to the screen. And as I say, I learned this information from Darryl Sloan's tutorial document here. So if you want to take a look at that, you can follow along with me as well. And also, as you probably know, if you want to follow along with me on your computer, I'm using the ZX Spin environment, and I have a video that explains how to install that and how to use it as well. And you can watch that video too if you like. So let's go ahead and take a look at how we can print a single character to the screen. So the first thing we need to be aware of is that by default, these lower two lines on the screen, those are the ones that are going to get printed to if we don't specify any other output channels. So we're just going to leave it in its default mode, and we're going to print to those bottom two lines of the screen. And the way we're going to do that, it's quite simple. All we need to do to print a single character to the screen is to load the A register with the code for that character. So first let me find a character that I want to print, and I'll do that by bringing over my ZX Spectrum basic manual, which is right here, and I'll scroll down to the part that shows the different characters, which is right here. The character set, which is in Appendix A on page 183. If you happen to have this manual, it's available as a free download PDF online as well. and I've also uploaded this PDF to the file section of the SpriteWorks Facebook group for my Patreon subscribers. So let me just take a look at this and see which character I want to print on the screen. So let's say we want to print which character? How about this copyright symbol here? So you can see this copyright symbol has a character code of 127. So that's very easy to print. All I need to do is go back to my assembler here, and the code for that character was 127, so I'm going to load that value into the A register by typing load A, comma, 127, just like that. And now I'm going to use a command called rst space 16. Now this 16 is a decimal number, and if you wanted, you could use the hexadecimal equivalent of this number, which is rst $10 in hexadecimal. And then I'll put a return instruction. So this is the entire program that we need to print a single character to the screen. And in this case, we're going to be printing the character that corresponds to code 127, which in this case is a copyright symbol. So let me go back and assemble my program now. And there my program should be assembled now into memory location 30,000. So let me go ahead and run the program. And I'll do it the same way that Darryl explains how to do it in his tutorial, which is just by running it the way it is, which is randomize user 30,000, and it's going to execute this code, which should print this copyright symbol on the screen. And as you can see, all we see on the screen is this OK message at the bottom. And the reason we don't see anything displayed, by default, the output channel that gets printed to is this lower area of the screen where these two lines are. So this message of OK is printing over the character that we just printed to the screen. So in order to be able to see that character print on those lower two lines of the screen, we need to modify our execution program a bit. And now I'm just going to enter a basic program, line 100, randomize user 30,000, and then line 999, pause 0. So now when we execute this basic program, it will call this machine code subroutine, but it will pause indefinitely before printing that message on the bottom two lines of the screen. So now if we run this program, we should be able to see our character printed on the bottom two lines of the screen. So let me go ahead and run that now. And there you can see our copyright symbol right down here. And the computer is waiting for us to press a key now, so I'll go ahead and do that. And you can see the message overwrites the symbol that we printed. So in this case, all we need to do is enter a pause statement to allow us to see the character that we've printed on those bottom two lines. So now if we want to print on the top part of the screen, this large section up here, which is known as output channel 2, we need to change our assembly language program to specify output channel 2, or the large upper part of the screen. And the way we're going to do this is by making use of one of those ROM routines I mentioned. Someone has thankfully written for us a nice routine in ROM memory that we can access that will allow us to change the output channel to the upper part of the screen. And we're going to do that first of all by loading the output channel number into the A register, and I'll do that by typing load A, comma 2, since we want output channel number 2, which is the large upper part of the screen. And then we need to call this ROM subroutine, which will activate this output channel for us. And in this case, the subroutine is located at memory address 5633. So all we need to do is type a command call 5633, just like that. So now let's go ahead and assemble our program again. And now that we've indicated a channel 2 output stream, which indicates the upper part of the screen, let's go ahead and run our program again and see what happens this time. So now we have our character printing on the upper part of the screen, which is output channel 2, which we specified here in our assembly language program, which we used to call subroutine 5633, which is a ROM subroutine, which activates the output channel that we specified, in this case channel 2, which represents the upper part of the screen. Now if we wanted to change that back to the lower part of the screen again, all we need to do is change this 2 back to a 1, and we could assemble our program again, and run our program again. And now you can see it's printing back on output channel 1, which is the lower two lines of the screen. So let's go ahead and change this back to 2 again, and reassemble. And now let's take a look at some other things we can print to the screen. So let's go back to our Sinclair Spectrum basic manual, And we'll take a look at some of these other characters. So if you take a look at the character codes, you can see that characters 0 through 5 here are not used. And then character 6 here says print comma. So this is actually a function of the print command. And there are some other characters here which are not actually characters, but they're functions. For example, here you can see ink, paper, flash, bright. These are all attributes that I'm sure you're familiar with by now. So what if we were to try and print some of these other codes to the screen, which represent not printable characters, but they represent some functions like this. So let's say, for example, we wanted to print character 18 here, which corresponds to the flash command. Would that make our character flash on the screen? Well, let's give it a try. So character 18 represents flash. And if we go back to our program now, let's modify our program by adding this character 18 ahead of this copyright symbol by again typing LD A, 18. And why don't I enter some comments into our program to make it more readable, which is what we should be doing when we're making programs anyway, right? So that they're easier to modify and easier to maintain, and just easier for us to figure out what the program is doing. So let's get some practice adding comments to our assembly language programs. So I'm going to start up here with line 2, where we load the output channel into the A register. And as you probably know, we enter a comment by using a semicolon followed by some text that is our comment. So in this case, I'll just say specify output channel 2, and I'll say upper screen. And then the next line here, where it calls the ROM subroutine to actually activate that output channel for the top part of the screen, I'll just say activate output channel. And the next line here, this is where we're going to be adding the flash command. We're going to be trying to print the code for a flash command on the screen. So I'll just type flash command. And now we need to actually print this code to the screen as well. And we're going to do that exactly the same way we printed the copyright symbol, by using this RST command. And this time I'll just use the decimal number for this RST command, which is 16. And I'll say output to screen. And then the next line here, we have a code 127, which we know is the copyright symbol. And again, on our next line, I'll again say output to screen. And this return instruction doesn't really need a comment, although it can be useful to comment return instructions as well, because you could have multiple return instructions in your assembly language program, and some return instructions will be returning from a part of the machine code program to a different part of the machine code program that called them. But in this case, our return instruction is returning control of the computer back to the basic program that called it. So here I'm just going to put a note, say return to basic. Just like that. But there's one more thing we need to add to our program, and can you figure out what that is? Well, with the flash command, we have to indicate the status of the flash command, whether we want that character to flash or not. So in BASIC, we would do that by issuing a flash1 command, which would activate the flash command, meaning we want the character to flash. Or if we use flash0, that would mean we want the character to not flash. So in this case, we've indicated the flash command with a code of 18 here, but we still need to indicate whether we want that flashing attribute to be on or not. So we want it to be on in this case, so we need to output the value 1, which turns on the flash command. And we'll do that right here after the flash command code by again loading A with the value. So I'll say load A, comma 1, and then I'll put a comment that says enable flash attribute. Like that. And of course we need to output that flash attribute to the screen as well using our RST command. So I'll type RST 16, output to the screen. Just like that. And now our program should be ready to assemble. So let's go ahead and do that. And I'm going to do it by pressing Alt-A this time, because we don't have to go up here to the File menu and click Assemble every time. If you want a bit of a shortcut, then you can press Alt-A on your keyboard. So that's what I'm going to do, press Alt-A. And you can see it brings up our assembly window. So now I'll press enter for OK. And our program should once again be assembled into memory. And now I can run our basic program, which calls our assembly language program. And there, now you can see our copyright symbol is printing on the screen and it's flashing. So that's pretty cool. We can actually print control codes to the screen as well as printable characters. So since that is so interesting, let's see what else we can do with these control codes. And I'm just going to go back to my manual here and see what other control codes we have. Well, right here, for example, code number 17 represents the paper color. So why don't we give it a paper color? We'll go back to our program now. And after this flash attribute, and I could put it before the flash attribute, but why don't I just put it after? So here, I'll enter another 2 lines of code. So now if we want to print our copyright symbol with cyan paper, we first need to output the code for the paper attribute, which is, if we look here, paper is control code 17. So let's go back and enter control code 17 by typing LDA 17. And then I'll put a comment that says paper control code. Just like that. And now we need to output that code. So again, I'll type RST16 with the comment output to screen. And now we need the code that actually corresponds to that cyan color, which is code number 5. So I need to load A again with code number 5. And I'll just put a comment indicating cyan paper color. And then we type our RST command again, RST16. And let's go ahead and assemble our program now. And now if we execute this program, we would expect to see a flashing copyright symbol with cyan paper. So let's give that a try. And there we go. We have our flashing copyright symbol with cyan paper. And so you can take a look at these other control codes here in our listing in our book. So if we wanted to, we could output a control code to specify the ink color and a control code to specify whether the brightness attribute is turned on or not. And we can even output positional codes such as at or tab, and we'll be taking a look at those in a moment. But first let's take a look at a simple one, which is right here, code number 6, which says print comma. So as we all know, for example, in BASIC, if we use a comma in a print statement, that moves the print position halfway across the screen. So why don't we try that in our assembly language program? So let's print a second character now after this flashing copyright symbol, and we'll do that by adding it to the end of our program. So the first thing we need to do is output that print comma code, which is right here, code number 6. So let's go back to our program and load A with a value of 6. And we'll put a comment indicating that this is a comma control code. And of course we need to output that to the screen using RST16. And let's choose another character to print here. So let's say we want to print maybe this hashtag symbol here, which has a code 35. So now we want to load the A register with the value for this hashtag symbol, which is code 35. But at this point, let's take a look at another trick we can use, which is instead of printing the character using its code, we could actually print the specific character by doing this. We can say LDA, comma, as we would normally, but this time instead of putting the code, let's put the actual character. And we need to put the character surrounded by quotation marks, just like this, and I'm going to put the hashtag symbol surrounded by quotation marks. And I'll put a comment here, which isn't really necessary because we can actually see the character we're printing, but we'll put a comment that says hashtag symbol. And now we need to output that hashtag symbol to the screen using our RST command, just like that, and we'll assemble our program again. And now if we execute this program, we would expect to see our flashing copyright symbol again, followed by a hashtag symbol printed halfway across the screen. So let's break into our program here and we'll run it again and we'll see what happens. And there we go. So it's actually printed both of them flashing and with cyan paper, as you can see here. Because of course we'd never disabled our flash or our cyan paper attributes. But in this case, we see they're both printed using flashing attribute and cyan paper because we never disabled those. And we could disable them if we wanted to. All we need to do is enter those values again in our assembly language program for the flash attribute and the paper attribute, and enter a value of 0 for the flash attribute and then a value of 7 for the paper if we wanted white paper, for example. But I think this gives us a good indication of how we can print individual characters to the screen. Alright, so far so good. So now let's see how we can print multiple characters to the screen. And we're going to do this by printing a string of characters. And this gets a bit more involved, but it's not really all that complicated, so just stay with me and we'll get it figured out pretty easily here. And we're going to start a new program, and this time what we want to do is print a string of characters to the screen. So the way we're going to do that is, first of all, we need our org statement, and I'll just use, let's say, address 40,000 this time. And again, we want to print to the upper part of the screen, so we need to specify the output channel as channel number 2, which I'll do by loading the value 2 into the A register. And I'll put a note indicating that's for the upper screen. And we need to call the subroutine that activates that output channel, which is routine at 5633. And now we're going to make use of some information that we learned in a previous video. And again, I'm just following along with Darryl's tutorial here. So if you want to follow along with me, you can go ahead and read the tutorial and you'll see exactly what I'm doing and why I'm doing it. So this next part gets a bit complicated, but it's nothing we can't handle, right? Because we've handled everything else so far. So now what we want to do is, when we're going to be printing a string of characters to the screen, there's actually another ROM subroutine that will help us to do that as well, luckily for us. But we need to help this subroutine along by passing it some values, and we're going to make our lives a bit easier by using information that we took a look at in our 2 previous videos, which is we're going to be looking at assembler directives, and in particular we're going to be using labels to help us indicate where those memory addresses are located. So just follow along closely and we'll be able to figure this out. And the first thing I want to do is, before even figuring out how to output the characters to the screen, is I want to just program which characters I want to print to the screen. So the way I'm going to do that is I'm going to use a define byte statement as we covered in a previous video. So first let's enter a label that indicates where our string will be stored. And what should we call this label? Why don't we call it string start? So I'll just type string start here. And you have to be careful not to use reserved words in your labels. So I'm just going to abbreviate my start word here by typing string strt, just like that. And now if I press enter, we can see it turns pink, and this indicates a label. So now what string do we want to print? So let's go to the next line here after our string start label. And as we now know from our previous videos, this string start label will now contain a value, which is the memory address where the rest of our code will start. So now let's enter the rest of our code that we want to print to the screen as a string. And if you're not familiar with how assembler directives and labels work in assembly language programs, you may want to go back and watch these 2 videos that I made on those subjects. So now let's choose which message or which string of text we want to print on the screen. And we'll do that by using the define byte instruction, which can be entered by typing DEFB for define byte. Or if we wanted, we could just type DB in this assembler. But I'll go ahead and type the whole word DEFB. And now I'm going to enter a string of text. So I'm going to start off with a quotation mark. And then I'm going to enter my string of text. And let's say I want to print hello, good sir, exclamation mark, just like that. And ended with a quotation mark. And there is my string of text that I want to print on the screen. But I want to make this a bit more interesting, so before I print this string of text, let's go ahead and print some control codes as well. And just as we printed control codes earlier to indicate flashing and paper color and so forth, let's go ahead and use the define byte instruction again before the string of text right here. And now I want to enter some control codes, and we can choose what control codes we want to use. So maybe I want to print this string of text at a particular location on the screen. So let's say I want to print this at location maybe 10, 3, as we would do in BASIC, which would be 10 rows down and 3 columns over to the right. So now we simply have to go back and take a look at our manual again and see what is the code for the print at function. Alright, so let's take a look here. And right here, code 22 says at control. So this is the print at statement. And we can use that in our assembly language program amazingly, but let's go ahead and do that. So we want code 22 to indicate an at statement. So I'll go back now to my program, and in this previous defined byte statement up here, I'm going to enter code 22 and then a comma, because we can actually enter multiple values after a defined byte statement separated by commas. So let's go ahead and enter some more values to indicate some more attributes we want to use for printing this "Hello, good sir" text message on the screen. So now this code 22 is going to tell the computer we want to print this message at a specific location, and now we need to tell it where we want to print. Now in BASIC, when we use the at statement, we would say, let's say I'll go over here to my BASIC emulator and I'll say print at 10,3, and then I'll put a semicolon and then a quotation mark, and why don't we print the same text here, which is "Hello, good sir," quotation mark. And so when I enter this instruction now, it prints "Hello, good sir" on the screen at position 10,3, which is 10 rows down and 3 columns over to the right. So we need to indicate that in our assembly language program as well. So that's very easy to do. All we do is enter those positional coordinates right here after our at code 22. So we want to enter the next positional code, which is at 10, which is row 10. So I'll enter 10 here. And then we need to follow that with a column number, which is 3. So I'll simply enter 3 here. And I'm going to put a comma because we want to enter some more codes to make this a bit more interesting. So what else can we do to this string of text? Why don't we choose blue ink on yellow paper and we'll make it bright. So first we need to specify ink, paper, and brightness. So let's go back to our manual here and we'll simply look for the ink, paper, and brightness codes. So right here we can see ink is code 16. So we'll go back and enter code 16, comma, and we want ink color of blue, which blue is color number 1. So I simply put 1 and then another comma. And now we want the paper color, which we want yellow. So paper has a code right here of 17. So we'll go and enter code 17. And then the code for yellow paper is color number 6. So I'm just simply going to enter a 6 here. And then another comma. And finally we want to make this print in bright. So we'll go back to our manual. And where is the bright code, which is right here? Here's bright, and it has a code of 19. And we'll enter 19. Followed by, remember, we need to put the attribute for this brightness command, which is 1 since we want it to be enabled. So we'll put 1. So now let's enter a comment line to help us remember what this line actually does. And I'll do this on a separate line since it's going to take a lot of space. So I'll just enter a semicolon here and I'll put at 22, 3, ink blue, paper yellow, and flash 1. There, so that comment now tells us what that previous defined byte statement will do, because we're not going to remember what all those numbers mean, probably, but now we can see by reading this comment that we're indicating a position of 22.3 on the screen with blue ink, yellow paper, and the flash attribute is set to 1. So we now have a label here, string start, which indicates where the start of our string data will begin in memory, but we also will need a marker to indicate where the end of our string is in memory, and we'll see why we need that in a moment. But for now, let's just enter a label which will be used purely as a marker to tell us where the end of this string data exists in memory. And I'm going to call this label string end. Just like that, I've entered string end. And remember how we used the EQU statement in a previous video to assign a specific value to a label? Well, we're going to use EQU again, but in this case, we're just going to use a single $sign after it. So we're not indicating any particular data that's going to be stored in that string end label, but that string end label is automatically going to be assigned a value representing the memory address, which is at the end of this string of data. And now it's time to do the fun part, which is creating the code in our program, which will actually print this string to the screen for us. And remember, we're going to be doing this by calling a subroutine in ROM. And in this particular case, this subroutine needs us to pass it certain values contained within certain register pairs. So the first value that it needs is it needs the starting address of this string saved in the DE register pair. So let's go ahead and do that now. We'll type LD DE, comma, and now we need the location of the start of our string of text, or a string of data in this case, because our string doesn't merely contain text, but it also contains these control codes, and we can print these control codes exactly the same way as if they were text. So where is the start of our data? And that's very easy to figure out. It's right here because we have a label indicating the start of our string of data, and that label is called string start. So we just enter the label name up here, string strt, just like that. And I'll put a comment here that says start of string to be printed. And now the next thing that our program needs is what the subroutine that we're going to call needs, which is it needs to know how much data it needs to print, which means it needs to figure out how long is our string of data. And that length needs to include all the bytes that we're going to print to the screen, including our text values as well as our control codes. And so we could, if we wanted to, count up all these control codes and all our characters and get a specific number that we could load. But in this case, we don't need to, because we used this string end marker to automatically calculate that for us. And you can see that method being used in Darryl's tutorial. And we're doing it exactly the same way that he outlines there. And the way we're going to do that is by simply subtracting the start value from the end value. And that will automatically calculate the length of these bytes of data, right? And we need to enter that value into the BC register pair. So I'll simply type load BC, comma, and then this formula that I just mentioned, which is the ending label minus the starting label. So our ending label is string end, and then a minus sign, and then string start, just like that. So that will automatically calculate the length of our data by subtracting the starting address from the ending address, which gives us our length. And in case you're wondering why we need to load these values into these specific register pairs, DE and BC in this case, that's simply because that's how the subroutine in ROM has been written. It's been written to expect these particular register pairs to contain these values in order for it to do its calculations that it needs in order to print our string to the screen. So I'll just enter a comment here which says calculate string length. And now our program needs one more line of code, which is the line of code that's going to actually call the subroutine which will print our string for us. And this particular subroutine is located at address 8252. So here I could put call 8252, just like that, and I could put a comment, ROM routine to print string. But why don't we make our program even easier for us to use by assigning a label to this value. So just in case we have a long program where we want to be printing many strings to the screen, we might not always want to refer to that ROM routine by its specific number. So why don't we assign it a label? So let's go down here to the end of our program and we'll enter another EQU statement with a label, and let's call this label print string. So I'll type print string, just like that, with EQU. And this time we do want to assign it a specific value, and this value is going to indicate where this ROM routine lives in memory. And in this case, it lives at 8252. So now we have a line of code that assigns the value 8252 to this print string label. So now up here, when we call this subroutine, we can call it using this label. So I'll erase this 8252 value, and I'll replace it with the label print string. And then finally, of course, our program needs a return statement, and I'm just going to put another comment that says return to basic, because in our particular program that's what this return statement is going to do. It's not returning to another part of the machine code program, but it's returning to the basic program that called it. So now hopefully I've entered everything correctly, and we'll see if this works. So I'll go ahead and assemble it now, just like that. And before we actually execute this program, I'm just curious to take a look at these labels to see that they got transferred over to our debugger correctly. So I'll open my debugger here, and I'll look at the Labels tab. And you can see here we have three labels that were brought over: print string, string start, and string end. And these are the values that they contain. String end contains a value of a memory address 40039. String start contains a memory address of 40015. And print string, of course, contains the specific value that we assigned it of 8252. So now let's close our debugger and we'll go ahead and execute this program. So in this case, I'm going to change this 30,000 value to 40,000 because we assembled it at address 40,000 this time. And let's run it and see what happens. And there you go. Luckily it all worked. I must have entered everything correctly, amazingly. So here we have our string of text being printed exactly where we wanted it to be printed, with the attributes that we intended, having a brightness of 1, blue text on yellow paper. And that's how we print a string of text, including attributes, to the screen. And I'm pretty sure that should come in handy in any games that we want to develop. Alright, so if you're still following along, that's fantastic. We're almost at the end, and the last thing we want to learn is how to print some numbers to the screen. Now you can probably figure out some way to print numbers to the screen just by looking at the information that we've already learned in today's video. And one way we could do that would be by printing the characters that represent the number characters in the character set. So if I go back to my character set here, obviously I could just scroll down until I get to the characters that are numerals. For example, here are the digits from 0 to 9. And if I wanted to, we could just print these characters the same way that we printed the other characters, using these values for the characters over here. Or we could use these exact characters contained within quotation marks, the same way we printed the hashtag symbol before, right? So if we go look at our program again, obviously we could just replace this string here with a number. So I could just put, let's say, the digit 8 in here, or I could put multiple digits, maybe 812, like that. And then if we reassemble this program and we run it again, now it prints the digits 812 on the screen. So here technically we're printing numbers, but actually we're not. We're just printing characters that look like numbers. We're not doing any calculations with these numbers. We're not able to manipulate these numbers at all, because we're simply printing these specific characters that happen to look like numbers. So what we want to do is be able to print actual numbers. So let's take a look at how we're going to do that right now. Now let's say, for example, you want to print the player's score in a game that we're programming. Let me go ahead and erase part of my program here. So I'm just erasing everything after these first commands that activate the upper part of the screen by setting the output channel as 2, which is the upper part of the screen, and calls the subroutine that activates the upper part of the screen, which is output channel 2. So now what we want to do is print numbers, right? So first of all, let's store a number in memory, in a memory location that we're going to kind of use as a variable in our program. And we covered variables in a previous video, which you can take a look at if you haven't already seen it. But obviously in assembly language, we don't have variables. We do have registers, but they're not really intended to be used as long-term variables. So instead, we're going to use memory locations combined with labels that we looked at in our variables video. So here I'm going to enter a label, and I'm just going to call it score. And I'll use the define byte directive, just like that. And now let's say our initial score is 100. So the player starts off maybe with a score of 100. So now what we want to do is figure out how we can print this score to the screen. Well, actually it turns out printing numbers is just as easy, if perhaps maybe even a little easier, than printing the characters. And the way we're going to do this, as you can probably guess, is by calling another ROM subroutine. And there's actually two different methods we're going to be using for printing numbers, and I'll explain why in a moment. So the first method we're going to use is by calling a subroutine located at memory address 6683. So I'm going to do that right here, and I'll enter a call instruction 6683, just like that, with a comment, and this comment is going to be print number. But in order to call this subroutine, we need to pass it a value in the BC register pair. So as you can probably guess, the value that we need to put in the register pair is the score. So we're going to do that right here using the LD command, LD BC, comma, and now we're going to grab the score, which is stored down here at this memory location, which is indicated by this score label. And we can see that we've used the define byte instruction to store a byte of data, which in this case equals a value of 100. So we want to grab the value that's in this score label, since the score label is pointing at a memory address, and we want to insert that value into this BC register pair. And that's very easy to do. All we have to do is put a bracket here and then put our label, which is score, and close the bracket. And I'll put a comment that says get score value, just like that. And of course we need to put our return instruction back at the end of our assembly language program, and I'm going to put that right here before our define byte instruction, because our define byte instruction is not an assembly language instruction that's going to get converted into machine code and executed by the computer. So now we have our entire program, which will extract this value that we stored in memory location to keep track of the player's score. It's going to put it in the BC register pair, and it's going to call the subroutine that will print that number to the screen. So let's assemble this program, and we'll go back here, and we're going to call this subroutine now, or execute our machine code program, and we should expect to see this number 100 being printed on the screen. So let's give that a try. And there we go, we have our value 100 being printed on the screen. And remember, the way we did that was by using this call instruction to call a subroutine in ROM located at address 6683 right here. Now, one thing we need to be aware of when using this method for printing numbers is that this particular ROM subroutine that we're calling here, 6683, can only print numbers up to a maximum value of 9999, so 9999. And the reason for that is because this ROM subroutine is actually intended for printing basic line numbers, which can only go up to 9999. So although we can use it for printing whatever numbers we want, up to that maximum value of 9999, it is intended actually for printing basic line numbers, apparently, so that's why it has that limitation. So let's just confirm that, and the way we're going to do that is by going here and modifying this value to print 9999 instead of 100. Now, you might notice a problem in me trying to do that, because here we have a define byte instruction, and a byte instruction indicates obviously 1 byte. So 1 byte can hold a maximum value of 255. So obviously I can't load 9999 into a single byte. So there are two ways that we can accomplish this. One way is to change this define byte instruction to a define word instruction, which represents 2 bytes, which will be able to hold our value of 9999. But before we go ahead and do that, let's look at another kind of more complicated way we can do that, just for completeness, because it's kind of interesting to know how to do. So these define byte instructions can actually be followed by multiple values. They don't just need to store one value after it. You can put a string of values after it, separated by commas. So we can do that by indicating, in this case, the 2 bytes that represent the value 9999. Now, the way I'm going to figure out which 2 bytes of data actually represent a value of 9999 is I'm going to kind of cheat a little bit here. So I'll show you a little trick we can use. If we go up here to our debugger tool again, and I'm just going to load this value 9999 into the HL register pair here by double clicking on this number and entering 9999. So now you can see the HL register pair in our debugger contains a value of 9999, and I'm going to go up here to the view menu and select 8-bit registers, which will split up our HL register pair into its individual 8-bit registers. And now you can easily see the H register contains a value of 39, which is the high byte, and the L register contains a value of 15, which is the low byte. So now if we go back to our program, we should know by now that machine code programs always store the low byte first, and in this case our low byte is 15. So I'm going to just erase this 100 and replace it now with 2 bytes of data that represent a combined value of 9999. And so we know our low byte is 15, so I'll enter 15 and then a comma, and then our high byte, which is right here, which is 39. So I'll enter 39. And Don't get confused because I use the HL register pair here to calculate what these values are for me. The HL register pair has nothing to do with our program. It's simply just a cheat I'm using to figure out what those 2 bytes of data are that represent the value 9999. And I could, if I want to, go back to the view menu and turn off this 8-bit register selection, and we can see that the HL register pair contains 9999. So although we're not actually using the HL register pair in our program for any purpose, it's kind of a neat way we can convert quickly back and forth between a 16-bit value and 2 individual 8-bit values by using our debugger here. So let's go ahead and close our debugger now, and let's try running our program again. So I'll assemble it here, and now let's try running it. And now you can see we get a value of 9999 displayed on the screen. So now let's go ahead and try the other method of printing this value by using the define word assembler directive. So I'm just going to go over here and replace this define byte instruction with define word by putting a W here. And so now this define word assembler directive can handle 16-bit numbers, which means we can put a number here that ranges from 0 to 65535. But in this case, we just want a value of 9999. So now using our define word instruction, I can enter this number directly as 9999, and then I'll go ahead and assemble the program. And now if we run it again, we should expect to see our 99 value come back on the screen, and there it is. So now let's go back and change our program to increment this value to 10,000. And we just want to do that to confirm that this subroutine is not actually able to print numbers this large, since 9999 is the maximum value. So let's reassemble our program now. And now if we run it again, it shouldn't be able to handle this number. So let's go ahead and run it and see what happens. And you see it gives us 3 zeros for some reason, so it's not able to handle a value larger than 9999. So how do we go about printing a number that is larger than 9999? Let's take a look at that right now. So it's not actually much more difficult than the method we're using now. All we have to do is add a second call routine to access another ROM routine that will be used to print larger numbers. So I'm just going to leave my define word value here at 10,000, and we're still loading the score into our BC register pair. But now instead of calling this subroutine at address 6683, we need to change this to 2 other values, and the first value is 11563, just like that. But now we need a second call, which will be at address 11747. So I'll enter 11747 here. And now if we use these 2 call routines combined with the value that we've loaded to the BC register pair, that should allow us to print numbers up to the maximum for 16 bits, which would be 65535. So let's go ahead and assemble our program again. And first of all, we'll see if it can handle this value of 10,000. So now let's run our program. And there we have our value of 10,000, no problem. So now let's change our program to go right up to the maximum value of 65535. And we'll reassemble now. And now let's try it again. And there we have our 65535 printing on the screen. And just for completeness, let's try incrementing this to a number that it shouldn't be able to handle, which is 65536. And we'll reassemble. And now, when we run it again, it gives us some random number, I guess, that's not able to handle this value. Actually, any number between 0 and 65535 will work. Let's say we want to print a small number like 3. We'll just change it to 3. Even though 3 isn't a word, it doesn't need 2 bytes to represent a value of 3. And it doesn't need to use these 2 call subroutines. We could easily use the single call subroutine that we used previously. But let's go ahead and try this, just to make sure that it works with small numbers. So now we'll run it again. And there we have our value of 3. Great, so now we can actually print the scores for our players in our game. And we have one more tool available for us now that we can use in making our games. Alright, so that's pretty cool. Now we've learned how to print both characters and numbers on the screen. And I'm sure that's going to come in very handy for us to make some games and print our players' scores and print all kinds of words and characters on the screen. And now I think we're finally ready. In our next video, we're going to be taking a look at that assembly language program that I mentioned, I think 2 videos ago, where we're going to be looking at printing both some characters and some values on the screen combined together. We're going to be revisiting labels and assembler directives, and we're going to put the whole package together to see how we can actually complete a challenge that I set for myself, which is a very simple task that we would normally do in a basic program. If we want to print, let's say, a character score, we want to print the word score followed by the value of the score, for example. Well, it's a little more complicated in assembly language, but now we have all the tools that we need in order to accomplish this task. So I'm going to give you this challenge now if you want to try it for yourself. So the challenge is to use labels to assign memory locations to store a player's health, gold, and strength values. And what we want to do is, first of all, print each of these values on the screen. So we want to print the attribute, which is health, gold, and strength, followed by their assigned values, which would be 100, 500, and 50 respectively. And then, just to make things a bit more interesting, kind of as a bonus challenge, in case any of you want to try this, let's try manipulating some of those values. So if you want to, you can give this challenge a try. And as I mentioned, you should have all the tools now to be able to allow you to do that. Otherwise, you're welcome to wait until I publish my next video and I'll show you my solution there. So we're going to be taking a look at that program in our next video. That's something to look forward to. And before we go though, I want to thank everyone for watching. I'm glad to have you joining me on this journey, and I really hope that this information is helpful to some of you who are interested in learning some tools for making your own games. So let's keep going and see how much closer we can get to making our own game. So that's it for today, and we'll see you next time.